talk about differential equations. The idea of differential equations is that, first of all, let's talk about equations. So, this you probably learned in algebra. You have something, a variable, and you do something to it, and you want to know what it's equal to. So in this case, it's pretty easy. You just solve for the variable. But imagine that you didn't know how to solve for the variable. What could you do? Well, you could guess. It could be like x equals 1, 1 plus 3 equals 5. Doesn't work. X equals 6. 6 plus 3 equals 5. Not true. X equals 2. 2 plus 3 equals 5. That is true. Therefore, this must be a solution. So in general, if you could guess a value and plug it in, then that would be a true solution. But in equations, we don't usually need to do this. Typically, there's a way to solve for a variable. In differential equations, they're a lot harder than algebra equations. So sometimes we have to guess, and sometimes we can solve for it. But there are many differential equations out there that we still don't know about. In fact, there's one called the Navier-Stokes equation, and if you can solve it, you'll get $1 million. So, what are differential equations? Well, you have a derivative. Remember, there's many ways to write the derivative. All these ways are sometimes useful in different differential equations, but for us, these are probably our favorite too, for differential equations. So, you have a derivative, and it's equal to something. Say, so this is probably one of the simplest and most important differential equations ever. So let's think about it and see if we can guess the solution. Well, let's try the function e to the x. We know when you take the derivative of e to the x, you get itself. So since you have one side that looks pretty similar to the right-hand side, maybe this would work. So if you take the derivative of e to the x, well, you have the right-hand side, it's equal to so you have e to the x equals a e to the x, so that doesn't quite work. But let's try a e to the ax. Well, oops. And this one works. Therefore, this is a solution. But it's just a solution. Remember, if you had an equation like x squared equals 4, you might try x equals 2 and see it's a solution, but it turns out x equals -2 is the complete solution. So when you talk about the solution, we have to account for every possible solution. So if you were to try, say, 2e to the ax, well, the right-hand side would be 2a e to the ax, and the left-hand side would be 2a e to the ax. So this would be a solution too. In fact, any multiple would be. Therefore, we write c e to the ax. In general, when you solve a differential equation, you get one constant. We call it an arbitrary constant. Now, typically when we have a differential equation, this is modeling some sort of real-world situation. In this one, this is called the exponential model. And it typically happens if you have like bacteria or something, and the more bacteria there are, the quicker they divide, therefore their rate is proportional to their actual amount. So you start off with just a little bit of bacteria, and then there's a ton. And typically, differential equations will relate something like this, and they're very good at describing real-world situations. You could also have something like radioactive decay, where you have the amount of say uranium is falling, and then the less there is of it, the quicker it falls, or the slower it falls. So it just gets to a really tiny amount. So typically we want to model real world situations. In this case, we want to look at initial value problems. And we typically want initial conditions, which means if we don't know how this thing started, for example, if this was bacteria, well, if there started out as 0 bacteria, then it would just remain 0 bacteria. If it started out as 10 bacteria, well, they divide really quick. If there was 1 bacteria, there wouldn't be so many at the start. So we need initial conditions. So typically we have something like y of 0 equals, say, 5. This is an initial condition. In this case, we know that if you plug 0 in for x, you're going to get 5, which means that e to the 0 is 1, so this just says c equals 5. Therefore, our solution to the initial value problem is y equals 5 e to the ax. And that's all there is to it. If you have an initial value, initial condition, you can plug it in and solve for the constant and get what you get your function that pertains to the specific situation. So in that case, if it was y of 0 equals 5, that means at time 0, if this was a bacteria model, there would have been 5 bacteria. So we like to have words that describe differential equations. This is called a first order equation. It's also linear. And that's it. So for example, if you have the 100 of y over dx to the 100 plus 3y squared d to the 5 of y over dx to the 5 plus e to the sine of d squared y over dx squared equals, let's put an x in here just for 3xy. This is a very complicated differential equation that we're probably never going to be able to solve, but we can talk about it. What is its order? Well, this is 100th order. To find the order, all you have to do is find the highest derivative. It doesn't matter where the derivative, what's being done to the derivative, or if there's other derivatives that are lower order. The order of the differential equation is the highest one there is. This is definitely nonlinear. And that's it. So we'll talk a little bit more about it later, but basically a differential equation is linear if only things like x's multiply the derivatives, and the derivatives are just on their own. So no taking exponentials of them, sines of them, and if a y occurs, then it would just be on its own too. Then it would be linear. Now this equation is linear. So, when we have first order equations, there's a certain type that we like, which are called separable. And it's separable if we can put all the y's on one side and all the dy's on that same side, and then all the x's and dx's on the other. So in this case, this one is separable. So we could write it as 1 over y dy equals a dx. And then we could integrate both sides. Then this becomes natural log. Lots of times they'll just say natural log of y, but we're going to be very specific. This is technically the natural log of the absolute value of y equals ax plus a constant. Now the inverse of the natural log, we could exponential it, e to the ax plus c, and then exponential addition, Now, let's look at this e to the c. It's always positive because whenever you take an exponential to a number, you get something that's positive. And if you want to undo an absolute value, basically you get rid of the absolute value bars and put a plus or minus out. So this is y equals plus or minus e to the c, e to the ax. Well, this thing was constant, or this thing was positive, but now we're plus or minusing it, so it could be positive or negative. And then you can also see that the special case of 0 works too. We could just call this y equals c, e to the ax. And this is the same thing we guessed. In fact, if you solve a differential equation right, no matter how you solved it, you should get the same solution. So here we were able to separate it. Lots of times they don't even bother with the absolute value or the plus or minuses, and the derivation just goes like this. But technically it's the absolute value in there. So in this case, our arbitrary constant came from integration. So other separable equations, well, sometimes an equation doesn't look separable, but it is. For example, this equation doesn't look separable, but if you just do a little algebra on it, now you can see that we could put all the y's on one side multiplying and all the x's on the other side multiplying. By the way, in order to be separable, it all has to be multiplication with the x's and y's. So integrate. And then solve for y. When you have to keep doing things to a constant, lots of times you can just rename the constant, or if you're not bothered by it, just pretend that the constant is like some sort of cookie monster that'll just eat things like constant multipliers and negative signs. And you don't even have to rename it, but we're going to. And then you can't just pull the constant out of this. You're taking the natural log of it. And this is the solution. So, for our separable equations, a separable equation is technically anything that can be written as this. And then we could write this as and then integrate both sides, and that's why it's called separable. So let's talk about another type of equation that's really useful and very easy to solve. These types of equations are linear, homogeneous, differential equations, with constant coefficients. So this is a lot of adjectives. So these look like this. Let's make this a 4, just for. So what's going on here is that you have some sort of differential equation, and then you just have derivatives added together, and then there's constant multipliers, constant coefficients. These are linear, and homogeneous means the right-hand side is equal to 0. It's not some function. And then this y here, well, how does this fit the pattern? The zeroth derivative of y is just y. So that's why this is really just the same thing. It's just a special case. It's a zeroth derivative. So how do we solve these? Well, let's look at a nicer one to solve. So let's try the method we tried before. Let's guess a solution. In this case, you have a bunch of stuff. Oops, that's important. This is y. Otherwise, this would not be a linear constant coefficient differential equation. Let's try and guess y equals c e to the ax. So if we plug this in, actually let's call it rx. You'll find out why we call it r. So we take the second derivative, we just plug it in, so we differentiate this twice. We use the chain rule. We get r squared. Let's write it this way. Now, all these have a common factor of e to the rx, so we can cancel those. And all these have a common factor of c, so we can cancel those. And now we're just left with an algebraic equation, r squared plus 5r plus 6 equals 0. And it turns out, if you guess a solution to a differential equation, and you have some sort of constant in it, and you have a parameter in it, and you get an equation that has no more x's, it just has that parameter, and you solve for the parameter, those solutions will be solutions to the differential equation. So this one we could factor. It's r plus 2 times r plus 3 equals 0. So r equals -2 and -3. So our solutions would be y equals c e to the -2x and y equals c e to the -3x. So it turns out we got two solutions, and that's actually okay. It turns out that if you take a differential equation, you're going to get n different solutions if it's an nth order differential equation. For most cases, for most like normal differential equations. And if it's linear, then they're just going to be what we would call a linear combination. So, since these two constants should be different, we call them C1, C2, and we can just add them. Why? Well, if you put this in, these derivatives just distribute over this addition. And basically these two will act independently of each other, and it'll be a solution. In fact, this idea is called superposition, and it's really important. It comes up in electronics, acoustics. The fact that if you have two solutions to the same linear differential equation, you can just add them, and you'll get another solution. So, we saw that the equation can be reduced to the equation where all we do is we take a derivative, a second derivative, and replace it with r squared, a first derivative and replace it with r, a zeroth derivative, and replace it with, that would be r to the 0, which is 1. This is called the auxiliary equation. And if you find the solutions to this auxiliary equation, let's write the general case. A d squared y over dx squared plus b dy over dx plus cy equals 0. We're dealing with second order. For now, we're just going to talk about second order, and then all that other stuff, constant, coefficient, homogeneous differential equations. Then this is ay squared, ar squared plus br plus c equals 0. Well, this is a quadratic equation. You solve these. It turns out that there's 3 cases. Case 1, we already saw this. You get 2 roots when you solve this. You get r equals r1 comma r2. Case 1, r1 and r2 are real. In this case, then you're just going to have a solution, y equals c1 e to the minus r1 x plus c2 e to the minus r2x. That's what we just saw. Case 2. Well, let's look at a special differential equation. I have to think about it. Well, let's see. Do this one. So, if you do this one, you write its auxiliary equation. It's r squared plus 5r plus 4 equals 0. Well, this can't be factored, so let's use the quadratic formula. You have r is equal to negative 5 plus or minus the square root of 5 squared minus b squared minus 4ac all over 2a, which is equal to negative 5 plus or minus 25 minus 16 is 9. Oh, wait, I messed up. This is just the case 1 equation. We don't really want to do that again. Yes, let's look at this equation. Okay, so r squared plus 4r plus 5 equals 0. R equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So this is equal to negative 4 plus or minus 16 minus 20 is negative 4. Now this is interesting. I'll divide by 2. Now, if you remember the square root of a negative number, well, this is an imaginary number. So if we have something like x squared equals negative 1, then this is x equals square root of negative 1, and the solutions are plus or minus I. I is the imaginary number. In this video, we're just going to assume you know what an imaginary number is. If you don't, there's all sorts of videos about imaginary numbers. So, this is negative 4 plus 2I over 2 and negative 4 minus 2I over 2, which is just equal to negative 2 plus I, negative 2 minus I. So we got complex solutions. That's a pretty different case. Well, let's see what happens. It's still true. You can still plug them into the exponential. So our solutions would be y equals c1 e to the negative 2 plus I times x plus c2 e to the minus 2 minus I times x. So remember that e to the ix equals cosine x plus I sine of x. This is Euler's relation, and it tells us that an imaginary exponential can be written in terms of trigonometric functions. If we do that for this one, for now, let's just write these as a plus bi and a minus bi. It turns out that these will always have this form. Then in this case, this becomes a plus bi, a minus bi. Then it also has the advantage of showing you what the general case is. Then this is y equals, exponential addition works even when it's imaginary, e to the a, e to the bi, well, we can factor out e to the a, and now let's use Euler's formula. So e to the bi is equal to cosine of bi plus sine of bi, I sine of bi. E to the minus bi is equal to cosine bi minus I sine of bi. So e to the a, this gets a little busy. So the proof isn't absolutely necessary, but it's kind of interesting, and it's really useful to know where it comes from. Cosine of bi. In fact, if you follow this proof, the general thing will be easier to memorize. C1 plus C2 cosine bi. Draw a line to separate what we did in the past, minus I sine of bi, which is equal to e to the a times, bring these things together, it's c1 plus c2 cosine of bi plus I c1 minus c2 sine bi. Now, these are just arbitrary constants, so we can take this, name it a, take this, name it b, and it's equal to e to the little a times capital A cosine bi plus capital B sine of bi x. Sorry about that, x. And as you can see, this imaginary unit, even as an arbitrary constant, it doesn't really matter. So our solution was real. So case 2, R1 and R2 are constants. The solution, they will be a plus or minus, R equals a plus or minus bi. You can see for yourself from the quadratic formula that R1 and R2 are always going to have this form as long as these coefficients are real. Then the solution will be y equals e to the a cosine bi plus a cosine bi plus b sine bi. So, in our case, we had a equal to -2 and b equal to -1. So the final solution would be y equals e to the -2x times a cosine minus x plus b sine minus x. And it turns out the minus you can just pull out a cosine and sine. So e to the -2x. Cosine is odd, so this is a cosine x. Sine is even, so this is still b sine x. Here we just absorb the negative into the b. So that's case 2. And finally, case 3, say we have an equation that looks like this. dy over dx plus 6 squared dy over dx plus 9y equals 0. The auxiliary equation is r squared plus 6r plus 9 equals 0. So if you factor this, you get r plus 3 squared equals 0. Well, this is different. This just gives us r equals -3 twice, a double root. Well, what do we do here? Well, we could plug in our one root, but we're supposed to have 2 independent solutions, and we only have 1. So it turns out that the other solution has the form x times e to the thing in the double root. I'm not going to try and prove this, but you can easily prove it to yourself by just differentiating this. And you can go look at more videos to see like a deeper reason why it's true. But we can also factor this and write it as c1 plus xc2 e to the -3x. So in general, case 3, double root, the solution is y equals r equals r1 c1 plus c2x e to the -r1x. So these are 3 cases, and of course you could have a complex double root. You can think about what you do in that case. You'd have a c1 plus c2x, and then it would be multiplying this cosine sine thing. So it turns out that there's a really important application of this in a lot of places. Physics. Consider a spring. You have some sort of spring, and it's mounted to a wall. It turns out that the equation can be written as m times d squared y over dx squared. We're going to use y and x, even though they typically use x for the dependent variable position and y for time. This is equal to k times y. So we could write this as d squared y over dx squared equals k over m y. In differential equations, it's very common to take a variable and rename it. So in our case, we're going to say that omega squared is equal to k over m. So basically, omega is just the square root of this thing, and we're going to plug that in because it turns out that it'll make the solutions a lot nicer. Now write the auxiliary equation. This is r squared equals omega squared y. It's easy to solve this equation. It's just a simple one. This is, this is the equation. It's just r equals plus or minus omega. So the solutions, in this case, this is negative. That's very important. So this is actually plus or minus I omega. So the solutions, here we have case 2, and we have a equals 1, b equals omega. So the solutions are y equals e to the, a equals 0, 0 times cosine omega x plus b sine omega x. And e to the 0 is just 1, so this is y equals a cosine omega x plus b sine omega x. So this is what this thing is going to do, and basically this is just a trigonometric oscillation, which means that x is time and y is position. So if you plot this, the spring, after it gets released, is just going to oscillate back and forth. For example, you take something and you just twang it. Well, not very many examples, but it's just going to go back and forth. So that's the equation in for what we call a harmonic oscillator. If we have air resistance, then our equation is going to look something like d squared y over dx plus b dy over dx. In this case, b is a factor related to air resistance that an object encounters, plus ky equals 0. And in this case, we're going to solve this. If we get, if we solve this equation, this is a spring that encounters air resistance, and we get case 1, then this is called overdamped. For example, a spring in molasses, and it's just going to decay exponentially, which means it doesn't even get the chance to oscillate much at all. If you get case 2, that's the most interesting one, underdamped. This one is an exponential multiplied by a trig function, which means it's going to do this. Typically, always in physics, the a here is going to be negative, which means we get an exponential decay. Otherwise, we'd have a spring that just explodes. So this is a trig function that's amplitude is decaying exponentially. And then this happens when you twang something like a guitar string and it vibrates for a while, but eventually it slows down and pretty much stops. And then the double Rick case is called critically damped. Which looks a lot like the exponential case, but it's not exponential because there's this x multiplying the exponential part. So this is these are probably the separable equations and homogeneous equations are two of the most useful things. Let's talk about a couple other ones. Let's talk about linear, non-homogeneous, I'm just going to abbreviate this. This is abbreviation for linear non-homogeneous differential equations with constant coefficients. So it's just like before. We'll have something like d squared y over dx squared plus 5dy over dx plus 6. But it's not going to be equal to 0. It's going to be equal to something like 3x squared plus 2. So what do we do here? Well, we're back to square one, and in this case we just guess. But before we do that, let's think a little bit. This is really important. In mathematics, we have these abstract functions called operators. So this whole left-hand side is an operator of y. So we could write O of y equals d squared y over dx squared plus 5dy over dx plus 6y. In this case, it takes any function, so you could put e to the x, you could put sine of x in, and you could do all these things, and it's going to spit out another function. So instead of being a function of, say, a number like 5, it's going to be a function of a function, which an operator. Operators are functions of more abstract things, like other functions or matrices or vectors. So in our case, the left-hand side is O of y, so we could write this equation as O of y equals 3x squared plus 2. Now, let's say we guess a solution to this. Let's call it y sub p. Well then, by definition, O of y sub p is going to make this equation true, meaning if you plug y sub p in, you're going to get a check mark, just like when you had 3 plus x equals 7, and you plugged in x equals 5, and you got a check mark. You were good. You guessed the right solution. Now, let's think about y sub h. Y sub h is going to be a solution to the equation O of y equals 0. This is a homogeneous equation, and it was like what we had before when we just said that this whole thing was equal to 0. So y sub h is the solution to this, so by definition y sub h equals 0. Now, these operators are linear, which means this is why they're called linear. This is why we use the term linear. It basically means that any two functions, O of f plus g, if f and g are functions, is going to be O of f plus O of g. This is what linear means. And it also means O of some constant times f is equal to the constant times O of f. So, if we plug y sub, here is something. What if we plug in y sub h plus y sub p? Well, O of y sub h plus y sub p, well, this is going to be equal to O of y sub h plus O of y sub p. O of y sub h is 0. Y sub p is equal to 3x squared plus 2. So this y sub h plus y sub p gets a check mark. It satisfies it. So the idea here is that you can take a superposition, that's what we call it. You can add up the homogeneous solution, so the equation with this equal to 0, and the non-homogeneous, the particular solution, a solution that you find, and that will be a total solution. In fact, when you solve for this particular solution, you don't tend to have any arbitrary constants, so all the arbitrary constants come in here. Because if you solve a differential equation right, you want the most general solution, which means if it's a second order differential equation, you want to find two arbitrary constants in the end. So this operator thing, a lot of people find it confusing, but it's one of the really important things in differential equations, especially linear homogeneous ones. So let's try and solve this equation. Well, it turns out that we can make a table of wisdom acquired over the years of good guesses for these equations. So We call this the right-hand side. We call this the left-hand side. So if your right-hand side is something, then we have a good guess in our table for it. So if your right-hand side is a polynomial, like a0 plus a1x plus a2x squared plus dot 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 an x to the n, then a good guess, well, you kind of guess the same thing. It just works out that way. Not always. This guess won't always work, but in general, it tends to. What about e to the ax? Well, it turns out e to the bx is a pretty good guess. What about cosine of ax? Well, it turns out sine of ax plus cosine of bx is a pretty good guess. In fact, this, in general, if it's cosine of ax plus sine of, I already used, actually I shouldn't have used a and b there, I just used them here. This should be c and d. Then this is a good guess. So, this table tells us that our right-hand side is of this form. So specifically, it's x squared, it's ax squared plus bx plus c. In this case, b is 0, but that's okay. So our solution should be something like bx squared plus ex plus f. So let's try this, but let's just use a, b, and c for the constants. So let's guess y equals ax squared plus bx plus c, and we'll see how it goes. So this is why a lot of people don't like linear non-homogeneous differential equations, but we're going to do it once. You got to plug this whole thing in. So this is going to take a while, so if you're really not interested to see me write all this out, you can maybe skip a little bit until it gets good again. Plus 10 ax like I said, a lot of people don't like linear non-homogeneous differential equations with constant coefficients. So you group the like terms. Now, these constants should equal the things on the left-hand side that are 0. So you could write this as 0x squared plus 0x plus 0. And then this should be this, this should be this, this should be this. So we have 6a equals 0, 2a plus 10a plus b equals 0, and c equals 0. This is a solution of, this is a system of linear equations. Luckily, this one's not too bad. We've already found c. A is clearly just 0. And then plug that in. So, oh, this is not 0x squared plus 0x plus 0. This is 3x squared plus 2. Yep, yeah, there's lots of places to misstep here. So hopefully this one's right. 6a plus equals 3, 2a plus 10a plus b equals 0, and c equals 2. So this one's already solved. This one is 2, and then you plug in 2 and 2, so you get 4 plus 10b and now we found A, B, and C, which were the original things we were looking for in our guess. This is our guess for the particular solution. So we have y sub p equals 2x squared minus 5/3 x plus 2. And now, this is our particular solution. Notice it doesn't have any arbitrary constants in it like we wanted, but that was okay. We know where we get the arbitrary constants from, which is the easy part of this problem. You just solve the homogeneous one, which is d squared y plus 5 dy over dx plus 6y equals 0, which we know how to do. It's r squared plus 5r plus 6 equals 0. We already did this one. The roots are -3 and -2. So the homogeneous solution is c1 e to the minus 3x plus c2 e to the minus 2x. So thus, the whole solution is y equals c1 e to the minus 3x plus c2 e to the minus 2x plus 2x squared 5/3 x plus 2. And we found y. So this is how you solve, in general, a linear non-homogeneous differential equation. So now we've talked about separable equations, we've talked about homogeneous ones, and we've talked about linear non-homogeneous ones. This is probably, this is a good start, and these are a lot of the differential equations you're likely to see. There's a lot more of them, but many things in real life, like bacteria and springs, can be done with just these ones.